and welcome to another session on sequential circuits. Today we'll look at the implementation of these circuits using state machines, state diagrams, and state tables. Remember that sequential circuits are logic circuits which depend on a previous input or previous output, as well as the present input to determine the new or next output. The synchronous sequential circuit uses a clock to make changes in the outputs and to proceed from one state to the next. State diagrams, such as the one shown on the right here, provide a valuable visual aid to express a state machine problem or a problem that requires a sequential solution. And they are the first step toward generating a truth table, also called a state table, and the subsequent implementation of these problems using digital logic. There are two different types of state machines to describe sequential circuits. In a Moore machine, the output is solely dependent on the current state, and that's shown here in that the state has a current as an output associated with it. S1 has an output of 0 associated with it, S3 has an output of 1 associated with it, and so on. So the output is solely dependent on the current state. In contrast, in a Mealy machine, the output depends not only on the current state, but also the current inputs. So here, in S1, we can have a different output depending on the inputs. For example, if we're in S1 and we get input of 0, 0, our output is 0. But if we're sitting in S1 and we get an input of 1, 1, we get an output of 1. So the output can change depending on both on what the present state is, S1, S2, S3, S4, and also what the current inputs are. So why would you use one over the other? Well, in general, a Mealy machine can be implemented using fewer states. And sometimes it can be faster because the output is computed immediately rather than having to wait for the clock to reach the next trigger or next state. A Moore machine, on the other hand, may be a little bit slower, but it avoids glitches at the output by clocking the output, so it's only available on a clock edge. The Moore machine outputs are also available for at least a clock cycle, so they wouldn't disappear shortly after a change in the inputs, as would be the case in a Mealy machine. Now, a state machine is usually described by a state diagram, and a state machine describes a problem that is sequential in nature and depends on the history or the previous states of the system to predict or to determine the present outputs. The state diagram describes the state machine and can be translated into a truth table that describes all possible input combinations and all possible combinations of the present states. The state table also provides the next states for all those combinations as well as the outputs. Once the state diagram is converted to a truth table or a state table, it can then be readily implemented with both combinational logic and either flip-flops or latches. Let's take a look at how this works. So here we have a state diagram that has 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. Those states require 2 bits, which we'll call S1 and S0, to describe them. There is one input in this state diagram or state machine, and it's the number shown before the forward slash in each state transition. And there's one output in the state machine that's shown after the forward slash in each state transition. Now we can look at the state diagram to fully realize the state table, which is the truth table that essentially describes the state machine and the state diagram. And we can translate one to the other by simply looking at the state diagram. Starting with the state 0, 0, here, if we now have an input of 0, we can see that our output is also 0, shown here in the transition, and our next state is also going to be 0, 0. If we're in state 0, 0, however, and we have an input of 1, in that situation, if we have an input of 1, then we'll go to state 0, 1 and do that with an output of 0. Now if we go to state 1, 1 and have an input of 0, which is here, 1, 1 with an input of 0, then we'll go to state 1, 0 with an output of 0. And if we're in state 1, 1 and we have an input of 1, we can see that we'll stay in the same state and have an output of 0. And we can continue the state table, filling out the state table in this way until we've exhausted all the possible transitions and states in the state diagram. That will give us the final state table as shown in this slide. Now the state table has several different outputs. It has the traditional output, out, which describes some function that's being performed by the state diagram, but it also has two other outputs that are the next state of the states S1 and S0. So in order to fully implement the state table, we need to not only come up with expressions for the output, but also expressions for all the bits that describe the next state of the sequential circuit. Now once we have a simplified state table or a fully realized state table, we can go ahead and simplify the expressions for the next state of S1, the next state of S0, and out using conventional techniques, in this case Carnot maps. Shown here is the Carnot map for the next state of S1, also known as S1 star. And we can come up with that expression, that simplified expression, by looking at the ones in the Carnot map to come up with a sum of products expression. And when we do that, we'll see that we have three groupings of 2 that describe the simplified representation of the output S1 star, or the next state of the bit S1. Using Carnot map techniques, we can come up with the final expression for S1 star. And S1 star is equal to in naught times S0, which describes this grouping of 2 in the Carnot map, or in naught times S1, which describes this grouping, and finally describing the last grouping, we get S1, S0. And that gives us the expression for the next state of S1 star. Now we can do the same thing for the next state of S0 or S0 star. Looking at a Carnot map now for S0 star in this next slide, we can do the same thing, and we'll come up with 3 groupings of 2 in our Carnot map for the simplified sum of products expression. And when we write terms for those 3 groupings, we'll have 3 terms, each containing 2 variables each, in our expression for the next state of S0. And finally, we need an expression for the output. And the output of this circuit only has one input combination that results in an output of 1. So the expression for out is quite simple. It's one term with 3 variables in it. Now to implement this is also reasonably straightforward, but let's take a look at how this works. So we're first going to implement the output, and we'll do that with combinational logic, which is very straightforward. In this case, we've been asked to just use 2 input NAND gates. So we'll put in and S1 into an AND gate, and then we'll want to AND it with S0 not. But in order to make these NAND gates, we'll double invert the output of the first AND gate to retain the same value, but to implement using NAND gates. And then when we do the output output of the last AND gate, we'll have to put it through an inverter to get the expression for out. Now notice that there are no flip-flops here. We've just implemented the expression for out like we usually do with a sum of products expression, and we've converted it to NAND gates using our traditional means for doing so. Now let's take a look at what happens when we look at the next state of S1 and S0, when things get a little trickier. In this scenario, first we see that we have three terms we're looking to implement with two input NAND gates. So let's start by doing that with the straightforward expression S1 not S0 into an AND gate, S1 not into an AND gate, and in S0 into an AND gate, excuse me. Now these would go into an OR gate, usually, but we'd like to convert this to a NAND gate, so we'll double invert the output of the AND gate, and that allows us with De Morgan's theorem to convert this now to a NAND gate. And then we'll go into the next OR function here, to get the next state of S0. But this is an OR gate and we need to convert it to NAND gate, so we will double invert. Now that gives us a NAND gate here, 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 and here. But we still don't have a NAND gate here, but we do have an OR gate with inverted inputs, so we can simply convert that to a NAND gate. And that now produces our next state for S0, for the bit S0. But what do we do with that? Well, in order to make sure that that's the next state, we'll have to delay it. And we'll just delay S0, or the next state of S0, by using a D flip-flop. And the output of that D flip-flop will simply be the present state of S0 that is then fed back into where it's needed for the present state of S0. And that's the implementation for the next state of S0, or S0 star. So what we've done here is use combinational logic to implement S0 star, and then used a D flip-flop to ensure that we delay S0 star so that we can use the present value of S0 in the expression for calculating S0 star. We can do the same thing with S1 using a similar technique, and once again implementing with two input NAND gates. We can get, first let's put S1 and S0 into an AND gate, and then we're going to OR that with in not and S1. Once we put it into an OR gate, we can double invert to get our NAND gates at the first stage. And then once we do that, we can convert the OR gate with inverted inputs to a NAND gate. And then we'll OR that with the last term, which is in not and S0. Those will also go into an AND gate, then into an OR gate. But now we'll have to invert the inputs of the OR gate in order to convert it to a NAND gate. Now this will become a NAND gate, and we're all set. So now we've produced S1 star, which is the next state of S1. And in order to buffer it from the present state of S1, we'll just put it into a D flip-flop once again, and the output of that D flip-flop will be the present state of S1, which will be fed back into our inputs for S1. So that's how we do the implementation of sequential circuits using present and next states, and using the state diagram and then the state table to come up with simplified expressions not only for the output but the present state. So the implementation of sequential circuits in many cases can be very straightforward. We can express the problem in a state diagram, make a state or truth table from the state diagram that includes both outputs and present states, and then find the simplified product of sums or sum of products for the outputs and the next states, and implement those outputs and next states using combinational logic as well as either D latches or D flip-flops, depending on whether we want the output to be state triggered or edge triggered. Well, that's all we have today for sequential circuits and their implementation using state diagrams and state tables. Thanks for joining us, and we hope you'll join us again soon as we continue to explore the world of digital logic and circuits.